This video will begin our discussion of section 2.4, something called exact equations. Let's take a detour real quick to kind of lead us into this idea. This is a Calc 1 topic. Sometimes Calc 1 teachers will skip over this section or give it lip service pretty quick. So I wanted to make sure you're good with this. Suppose f is differentiable in an interval I containing the point A. Cool. The change of f between 2 points, A and A plus delta x, right, change in x, is approximately, we have that. This is what's called a differential. Maybe that'll ring a bell. Differential. Now, probably no I in there. Texting has ruined my spelling. Differential, maybe? Something like that. Okay. Um, got the point anyway. Sometimes, though, we take it from there and we say dy is equal to f prime of x times dx. Right? And then sometimes this isn't like something really like we shouldn't be splitting a derivative, but we could think about it that way, right? Like we wouldn't really want to switch separate dy dx unless we're going to do separable or something like that. Okay, so that is from Calc 1. We get this, it's called differential. Um, Calc 3, I know some of you guys probably they don't require it before this, so I want to make sure in 3 space, when I have a function of f, then we can find the differential for z by taking the partial with respect to x dx and the partial with respect to y dy. So it's just a little bit more because I have two different types of derivatives in 3 space. I have a lot of derivatives, but x and y directions are important ones that we focus on. Okay, this new method to see how it works, consider a solution to a DE. So let's say this is some function, right? That was the answer that we got to in the end, right? This function right there. We can create a diffie by that by just differentiating both sides. So notice this is kind of what that set up there. Take respect to x dx and take respect to y dy. So notice that the derivative with respect to x, the 2 comes down, I get 2xy. The other two, y squared and 5, don't have x's, it's gone. X squared y, the y just goes away because it's with respect to y, minus 2y, and then 5 didn't have anything. So this results in a diffie that comes from partials. We know that we take the function and we take partials, we will get the diffie, right? So we're going to have a full method for this and how to test to see if this is true or not. I'm going to give a very simple case here. So consider this y dx plus x dy equals 0. And then we know that, okay, so I'm going to try to write this out here. And it's partial, d dx times something dx plus d dy times something dy equals 0. So we have to sit and kind of eyeball it for now because I haven't given you a method. Okay, but we can kind of think this out. This is some function, and when I take the derivative with respect to x, I just get a y. It would make sense then if that was just an xy, because when I take respect to x, y is considered the constant, so it stays. And then if I put that here as well, notice the partial derivative with respect to xy gives me an x. So there's our function, which means the solution to this equation is xy equals c. Because that is the function that when I take my derivatives, I get the one above. Now, this wasn't too bad, and maybe some of you guys are like, I don't know if I would have got there. I have high hopes that you guys saw it probably before I said it. But sometimes that's really difficult. That's in there, and eyeballing it is not going to work. All right, so let's talk about a method to get to our solution. All right, so here's our differentially expression, right? Is an exact differential in region R of xy plane if it corresponds to the differential, oh, I did spell it right, of some function f defined in R. That's what we just said, right? That I can take my partials and get this diffie. Okay, first order diffie of the form is said to be exact if the expression on the left-hand side is an exact differential. Okay, cool, that doesn't help us, right? I know I got to get to that. Now, I want to recall this property here. This is from Calc 3, ends here. Okay, assume that f is defined on an open set D of R2, that's some disk, right, in the xy plane. And we have a z going up. The mixed partial, so this is the partial with x, then the partial with y, and then the partial of y with the partial of x, different order, are continuous throughout D. So as long as they're continuous, then we have equality. So those are exactly the same. All right, so bear with me. I'm going to try to make a point here, okay? So f of xy equals c is our function. That's our answer. And then I know to get each one, I'm going to do f with respect to x dx plus f with respect to y dy equals 0. That was my Diffie Q that comes from that solution. Now, if I'm lining this stuff up, though, you can see that mxy is the same as that, right? And then nxy is the same as that. So I took we took f, and we got fx equals n. All right, so and then we have fy equals n. And then remember, this is where we're headed. I know these two things are equal, so what I'm going to do is take another partial, but that means I have to take that partial. Same thing here, fyx equals nx. So if those two things are true, like we said down here from Calc 3, then my must equal nx if exact. So it comes from, we don't really see it in our formula. Like when I see a diffie q like this, I'm not like, oh, that's telling me it's the first derivative of some function. No, it's not going to tell us that. We just know we have to check. And the way I have this is, notice that m is in with the x, so I take it with y, and then I do the opposite with the nx, right? I do n with the x, even though n is in the quote unquote y space. All right, so from there, and we just stated it, but if m and n they're continuous and have continuous first partial derivatives in a rectangular region are defined by that, okay, then a necessary and sufficient condition that that equation may be exact differential is this. And that's exactly what we just wrote down, right? Y partial, x partial. So to check if, I guess therefore would not be a good thing here, probably imply. If that's true, then it is an exact equation. And we'll come up, I'll show you the method for that. All right, we're gonna do a few examples. So it says solve the differential equation. I'm gonna write down the things just to make it clear. M in this case will be y cosine x plus 2xey. So I'm gonna take the partial of that with y. I'm checking for exactness. So I get cosine x plus, and then that thing just repeats itself, right? I get just the same thing. N of xy is sine x plus x squared ey minus 1. So that means nx is going to be cosine x, and then the 2 comes down, and I get the same thing. So therefore, the dE is exact. All right, I'm going to write a statement here. If you've taken Calc 3 with me, this statement's going to feel very familiar. This probably is ringing a bell anyway. This is the same as doing finding work inside a conservative vector field, if that rings a bell for any of you guys. If not, you're okay. We'll be fine. Okay, so since it's exact, then I know that some function exists. I'm going to write that down. Then, okay, I'm going to use some symbols here. There exists. I'm only going to write this one time. There exists. Let's math for it. A function f of xy such that if I take the partial of f with respect to x, I get m. And if I take the partial of, that's not a 2, by the way, that's my differential symbol, a y, I'm going to get n. So we have that. That's what we got from it being exact. Okay, so what that means, though, is I can work backwards from this. So then, I like to write sentences. It's the way formal math goes. So if you don't like doing that, just make sure your stuff makes sense. Then I can actually find this xy, f, by taking the integral of m with respect to x, right? Because if m is a derivative, to go back, I would take a integral. So I'm going to throw m there, y cosine x plus 2xey dx, right? Thankfully, they look daunting, but the y's we're just going to ignore. They're considered constants. The integral of cosine is sine. And then the integral for here, I go up by 1, which is 2 divided by 2. So I x squared ey. And then this is the weird part. Usually we would put plus c. But in this case, it could be some function of y, right? So for instance, remember, this is our function. So I'm going to write this down so we can see it just in one line. All right, so there is the function right now. All right, and the problem is we don't have the whole function. I'm going to explain this h of y thing real quick. If this was my function and I took the derivative of f to get here, if there was like a y squared or something down here, a y squared or plus y or minus y or something, it would have gone away with the x. So we have a function of y, which also could include the constants as well. So I'm going to take that function now, what we just came up with, and we're going to do f of y. So if I do f of y, okay, I get sine x plus that thing just comes out again, and then h prime of y because it's y. Then I'm going to set this equal to n because I know they have to be the same, right? If I had my original function and I took y, then I should get n. So I'm going to set it equal to n, which is sine x plus x squared e to the y minus 1. So that would mean that h prime of y is equal to -1. Everything else canceled. In this step, if the whole, you should only end up with y's. If you end up with an x, you did something wrong or it wasn't exact and you messed up. So if this is the case, to go backwards, I have h prime. To get h, I just take the integral. So I'm going to have a -y, and now I have a constant. So this actually gets us to our answer. We have f of xy. It's going to be y sine x plus x squared ey minus y plus c. But to get our solution, what we're going to do, and I know you're going to be like, why isn't it? Here, let me get to it. X squared e to the y minus y, and we're going to say equals c. But you might be like, why wouldn't it be -c? Well, -c is just a different constant. We haven't defined that constant at all. So this is our solution to the diffie-q. This is self-checking. If I take the derivative of that with it respect to x, I better get m. If I take the derivative with respect to y, I better get n. So you should be able to check these as you do them. If you've had Calc 3, this feels very familiar. It's the exact method for that other topic. So if you can find a shortcut, there is a way to kind of eyeball this. If you can do that, that's great. You can skip all this work, but I need you to explain something on your assessments, right? On your exams, explain something that you're doing. You have to explain your process. The reason being is if you get it wrong, one, if you just write down the answer, I kind of assume you're cheating. I mean, it depends. I can't push that because I don't have proof. But I don't want to assume that at all. I want to give you partial. Just explain your reasoning somehow on your paper. Okay. Oh, I always get go back. I always get this question if I need to um, write everything I did down. No, but the only things that were kind of unnecessary was like maybe this whole sentence here, but I use that to help. But it just these English words. That's literally it. Everything else is required, part of the work, unless you can eyeball it. There's a way to eyeball it. I don't want to teach you that. I want you to come up with yourself. That way you are learning the concept and making it easier for yourself rather than me just showing you the shortcut.